Hello again, everybody. My name is Pixel Rain, or Rain for short, and today I'm going to be showing you how to update your code to produce terrain like this. I'm going to be doing things a little bit differently today because there is a lot of changes required from our previous build to this. But as you can see, I am getting 300 to 400 FPS on average, and this is rendering at, double check, 64 by 64 chunks with a max height of 256, as you can see by these mountains here. So without further ado, let's get into all these changes. I'm doing this, like I said, differently today because these are all of our changed files. What I'm going to do is I'm going to start with one section and go over what's been changed or added. So to start with, I added a simple free fly camera. I believe this was from a Unity script site. I don't remember which one off the top of my head. Fairly standard free fly camera. Cursor locking, rotation, movement, simple stuff. And then we'll get into the noise functions, what actually makes it look pretty. So to do that, we'll start over here at our height map noise compute file. And as you can see, I added a new struct at the start of this called noise layer, and this is just going to control our noise settings like gain, frequency, linearity, persistence, octaves, and so on and so forth. I also made another struct called heighten noise. That's just a return value because you can't pass tuples or anything fancy back in compute shaders. And then I have a structured buffer where we take in the noise layers from the CPU. I changed our container sizes to unit. I changed our container size to a unsigned integer. Um, Added a noise count so that we can iterate over our noise layer buffer if we add more and start layering our noise. I also added a seed value because when you're generating 2D noise, you can use the Z position as your seed essentially. So you'll take your X and Z coordinate, run it as a float 2, as you'll see in a little bit, and then the Z for the 3D noise function can be your seed. I added two new fractal noise functions here. One is your standard, like this is pretty much the same function that you'll find on IQ's website. And then a second fractal function. They essentially do the same thing. They run through octaves that you define in your noise layer and then sample the noise at each point per octave, multiply your position by the linearity, increase the amplitude, or actually, I'm sorry, decrease the amplitude by persistence because persistence is traditionally a value between 0 and 1. And then it squares it and returns the value between 0 and 1. Pretty simple stuff. And then we have here a height and noise function called sample height at position, or at point, I'm sorry. And what this will be doing eventually is iterating through noise layers to produce fancier terrain than what we've got right now. But for the moment, it's working pretty well. So we just call our fractal noise function and then clamp that times 240 to between 0 and 250. So that'll take our 0 to 1 value and multiply it upwards of 240. So terrain can reasonably be between 0 and 240. And then we return that height rounded to an integer. And then we get the noise index ostensibly for our layers when we add them and return it. Moving down to the fill array function, or where the actual magic happens here. We set a new height and noise struct and then immediately set it by calling sample height at point. We set an unsigned integer called terrain height to be that height value. Our noise layer is derived from the other return value from height and noise. Nothing is particularly changed here. It's mostly subbing out to the terrain height value and changing the noise layer to return the selected noise voxel IDs. So we do our coloring from the noise layers. I will go over that script here in a second. And then we check our cave generation by using that other fractal noise, the more traditional one. And we pass in terrain height here so we can modify the multiplier that's used. And then if our value is higher in our cave threshold, it's now air. Moving down a little bit, we just assign our voxel ID and then assign it back into the array. Not too bad, quite a few changes, but not too bad overall. So then we will head over to our noise layer just to show you the C# side of the struct. Pretty self-explanatory here. And then we're going to go ahead and go over to our world manager and we're going to set up our threading. Told you, a lot of changes this video. So we've got a whole bunch of new usings up at the top. We have collections concurrent, threading, Unity mathematics, editor use, and profiling. I believe editor use is for profiling specifically. And then we now have a public transform for the main camera so we can track its position as it free flies through the map. We have a private vector3 to store it, and then one to check against so we're not constantly checking the loaded chunks. And then we have two concurrent dictionaries, one for modified voxels, which we are not using yet. That is going to be how I plan on handling saving, and that is going to be how I plan on handling saving and chunk manipulation, terrain editing, what have you. And then we have our active containers dictionary. As you can tell, I like object pools. They're pretty nice. They make things run faster. This keeps track of all the active containers in the map. We have our queue of unused containers that we can pull from. Then we have two more concurrent queues that are for when we encounter off thread that a chunk either needs to be made or unmade, deactivated. It'll get added to those and then processed on the main thread. And right here we have the integer defining how many of those we process per frame, because if we change that to 20, it will drop our FPS into oblivion. We have our main thread ID, our actual thread that we do the chunk checking on, a boolean to make sure the while loop dies if we close the program or we just want to kill the thread, and then a bool for making sure first pass has been done. First pass is what's going to generate that first 64 by 64 or whatever your render distance is in chunks. I've also moved all the initialization into its own function called initialize world. And this is what that looks like here. I get a integer for render size plus excess, which is render distance plus 3. And then I multiply that by itself to get the total containers that we want to pool to start with. So if your render distance is 16, that'll be 19 times 19 chunks that generate. So as you move, we're not generating new chunks. It has that little bit of a buffer layer in between. Then we initialize our compute manager with 6 times 3. It's currently 6 because I apparently didn't change it to be max chunks to process per frame. It seems to be that number times 3 is the amount of buffers we need, period. So if we try to do render size plus excess times render size plus excess for our buffers, it will throw your memory through the roof. We initialize our queues and dictionaries, and we get the thread ID of the main thread so we can verify if we're on main thread or off of the main thread. And then we generate our containers. Then we initialize our chunk checking thread, which is pretty simple. If you've never done threading before, you initialize a new thread to the function, which is going to be a loop. You set the priority and then start it. I use below normal because we really don't want it impacting performance in any way. And then down in update, we've got our main camera transform position doesn't equal the last updated position. So if our actual position doesn't equal our cache position, then we can go ahead and grab the new one that is used during the threading, because you cannot access a transform from a background thread. Unity is not threading friendly in any way, really. And then we have a while loop to make sure any containers that need deactivated are deactivated regardless. It doesn't impact performance much, and if we don't do that, it might create a situation where we need to create new containers, and we really don't want to do that. It's a lot of allocations to do that. And then we have our actual chunk processing. If we have containers that need creating, we'll go ahead and grab a new container, set the position to whatever position it needs, add it to our active containers, and then we'll call generate voxel data. Moving on to our actual threaded loop here, we've got a little bit of profiling that I'm probably doing incorrectly. Then we've got our half render size, and then a render dist +1. These are both used for bounds calculations and the loop to check active containers. We've got our actual bounds here, render dist +1 times container size and render dist +1 times container size. What that'll do is down here below, if a chunk is outside of that boundary, we'll deactivate it. We don't need it anymore. And that boundary is centered over our camera. Then we've got our basic while loop, and if our previously checked position doesn't equal the last updated position, or if first pass hasn't been performed, we'll go ahead and run our render loop here. So what it does is it takes negative half of the render size, less than half render size, same for z, and it calculates the position .x and z based on container size and our actual camera coordinates here, and then it adds it to the containers need creation queue. And then we set our actual bounds center here so that our bounds move with the camera as we move, and we iterate over all active containers, and if the container is not within the bounds, we deactivate it. And then at the end of that, we sleep for 300 milliseconds, so we're not just spamming this constantly in the background. It won't make it past here unless you've actually moved out of the chunk, but no reason to do vector 3 comparisons. It's not very efficient. Moving on, we have our container pooling, which is going to be the same pretty much across the board for how I do pooling. We have a get container method. If there's any available in the pool, we'll return it. If not, we'll generate a new one. And then here's our actual generate container function that's also called up at the top for generating the initial pool. Just creates a new game object and adds the component container to it, sets the parent to the world manager, and the container's local position variable to the position we need it at based on the queue, and then it initializes it against that, which sets our material and double sets the position, because why not be thorough? And then if we're trying to enqueue it to the pool, this is only really run up at the startup. It'll enqueue it to the pool, and then we return it. We have a deactivate container method that checks if our active containers has the position. If it does, we'll try and remove it, outputting it to a container. Then we'll clear the data on it and queue it back into the container pool and set it as inactive. We've got a handy little helper function down here called position to chunk board. All this does is divide the position by container size, so 360 divided by 16, and then it floors that position and multiplies it again by container size, giving us the flat chunk coordinate of that, which would be, let's see, 360 divided by 16, so 22, so we'll do 22 times 16. So 352 would be the starting coordinate for that chunk. Then we've got our application quit, just making sure we're cleaning up our threads, making sure it's killed, and then disposing of any of the active containers. I had an issue where the editor was retaining too much memory between runs, so my editor was getting up to like 14 gig in RAM or more. So I had to go through and do a lot of this cleanup kind of stuff. Then down here in world settings, we added a render distance setting and a integer that's got a get accessor on it, and all it does is return the total voxel count per chunk. Moving on, we'll head on over to our heavily modified container here. Alright, over here in the container file, I'm not showing the diff for this one because there's just a lot going on. A lot of stuff was removed. So what we'll do, we have our initialize still, where we configure the components, initialize our mesh data, and set our material and container position based on initialize. Our clear data function makes sure the meshes assigned to our mesh filter and mesh collider shared mesh are null, and then we call clear data on our mesh data. We've removed the generate mesh function entirely, and all we have left is the upload mesh, which if the mesh renderer is set to null, we'll configure our components, and then here's where the new stuff comes in. The stuff that makes us be able to generate a bunch of terrain really fast. So we've got a integer array of 2 called face count. It gets the data from our count buffer, and which is a struct of compute buffers. We'll get to that next. Then we get the data from our vertex buffer into mesh data.verts, index buffer into indices, color buffer into color. And now that we've got our mesh data locally, we can go ahead and assign everything to the mesh. It's pretty straightforward. I think this is almost the same code as before, just moved up into upload mesh instead of in mesh data itself. Assign our mesh filter and mesh collider to the new mesh. Scrolling on down, we've got accessors that are not used yet, but I plan on using in the future. And then this is what our mesh data looks like currently. We've got an array of indices, vertices, color, and our mesh, as well as an array size, which is just used to initialize everything. Our array size is set to max triangles, which is the max number of vertices, triangles, and whatnot we expect to have in a single container, which is container size times max height times container size divided by 4. I've played with the numbers a little bit. If you go too much higher, like divided by 6, occasionally you'll have too many vertices generate, and that causes problems with the mesh not being able to actually render. That's what works. It's not super efficient memory-wise, but it's getting there. Then we've got our clear data function, which clears the mesh, destroys the mesh, and then makes sure our reference to it is set to null, because GC gets allocated really weirdly, and I spent quite a while trying to keep it down. Now we're going to head over to our compute manager, one of the last, actually it looks like the last C# script we have. And we'll start with the mesh buffer, which is going to be very, very similar to our noise buffer, where we've got our compute buffers, one for vertex, one for colors, one for indices, one and our actual count buffer. We call initialize on everything, just generates our basic buffer. So our count buffer is a buffer with the size of 2, stride of 4. We set the counter value to 0, and we want to set the data to 0 by 0 just to be safe. GPUs are weird. Sometimes you'll get caching in between runs, and it's never a good time. We've got the same max tries calculation here that we did over in the container, and then we initialize our buffers based on max tries times 3 and then our strides. And then we've got our dispose function that just disposes of all the compute buffers. Jump back over into the diff here. So at the top, we've got our new compute shader variable, a private list for the mesh buffer, and a queue, one for all of them, one for available ones that we can pull from the buffer or from the object pool. We've got 2 new compute buffers, one for noise layers array and one for voxel colors array. This is again just that noise layers struct that we set up to pass into the voxel compute shader. And then we've got our voxel colors that we pass into the GPU as well. This is just a debug integer for the number of mesh buffers that are being generated. I don't think it's actually in use right now, but it's good to have something to keep track of if we're over generating. Then we've got our noise settings, seed, and our noise layers array. Then we've got a conversion function where things are going to start getting a little complicated for some of you, including myself, because I don't like bit shifting. So it takes in a color 32, which if you didn't know is a color with values between 0 and 255, which means RGB and A are all bytes. So that makes color 32 the same size as one integer, as opposed to 16 bytes or 4 integers / floats size-wise. So the way it runs in the shader requires me to change any 0 values to a 1, because it doesn't like bit shifting a 0. You can't bit shift to 0. And then the actual bit shift just shifts the R value 24 bits into our float, G 16 bits in, B 8 bits in, and then writes A in the free 8 bits at the end. Because, and I'm going to explain this really poorly, a float has 4 bytes worth of size, each taking up 8 bits in the memory, and each of these is a single byte. So we just shift it 1 byte into the float and combine it all into a single float. Scrolling down into our initialize function, we initialize our noise layers array and just set it based on our noise layers array. I know, the naming is not great. Then we've got our set integer for the seed going into the noise shader, and our actual buffer and layer count being set into our shader as well. Here we convert our world manager's colors to be a voxel color 32 struct, which I didn't go over, but I will in a second. Essentially, it's the same thing as before, except it's 3 floats instead of color float float. Then we assign that array to our voxel colors array buffer, and we assign that to our voxel shader, which is where we're going to be generating all of our mesh. And then we set the container size on our voxel shader as well. Let me jump over and show you the voxel color before I forget. So this is what voxel color 32 looks like. Like I said, almost identical. It just takes a float color instead of color. Back in our compute manager, we've got our create new mesh buffers being called in our initial pool generation. Remember, we should only be creating about 18 of these. And then down here, we've got this single function called generate voxel data. I believe this is taken from the compute helpers region of the noise buffers, as you can see over here. I just combined the mesh functionality and the noise functionality into a single function because we're using async callback. We go through our normal setup for our noise shader, assigning all our values, and we dispatch it. So one change is the noise buffer is only touched by compute manager. So we get it at the start, we set the counter value to 0, wipe out the internal data entirely, and then we assign those buffers into the noise shader for this run, set our other variables, and dispatch it. And then we queue up in the background essentially our voxel shader that actually generates our mesh data by doing the same thing. We'll get a mesh buffer from our pool, set our counter to 0, assign our other variables, including all of our mesh buffers here, and we dispatch it. And then here is where the magic actually happens. Once this finishes running, it'll kick off this async callback, which all it does is verify that our active containers contain the position that's passed in to generate voxel data. And if it does, we'll call upload mesh on that container, which gets all the data from our GPU buffers and initializes our actual mesh. And then once we get that taken care of, we clear and requeue the noise buffer and mesh buffers. Clear voxel data, I believe, is the same as it was before, where we just set our count to 0, and then we just wipe out all the data in the buffer with that second kernel in our noise shader. And down here, we've got our mesh buffer pooling. We've got our get mesh function that if we have any available, we return that. If not, we generate a new one. And then we've got our create new mesh buffer, which all it does is create a new mesh buffer, initialize it, then we add it to the list of mesh buffers and enqueue it if that is what was requested. Then we increase our number of mesh buffers counter. It is being used. I thought it was. And then we've got a clear and requeue buffer function for a mesh buffer as well. Doesn't actually do anything because of the counter value. So even if we generate less vertices on a new chunk, because we're counting up as we add vertices to it, our counter value is what lets us pull data from the GPU, so we're only pulling the amount of vertices that are generated by the dispatch. It doesn't matter what was on there before, what else is in there after that. Say we pull 1800 vertices, we only care about those 1800. Nothing else matters in that buffer. We have added our voxel colors array and our noise layer array buffers to the dispose function. And then we also added our mesh buffers to the dispose function. Moving on to our initialized buffer. I no longer have a voxel array index array in our noise buffer. So I took that out and then I generate a new noise buffer with the chunk count that we saw in our world settings and a stride of 4. And then we're back down to our mesh buffer. So that's it for Compute Manager. Now we're going to move on to our actual voxel generation here. These are both our compute shaders. And these are just the same static variables that are used in our containers mesh generation, but modified slightly for the GPU. So, float threes, completely initialized size, all that fun stuff. But it's all the same otherwise. And on to the fun stuff. So this is our voxel compute shader. This is where all the actual magic happens. It's pretty much the same thing as container, just modified a little bit to work on the GPU. So we've got our voxel color 32 struct and our voxel struct to receive those from the CPU. And then all of our buffers here. So we've got our voxel colors buffer, our array buffer for the voxels themselves, vertices, color, index, and counter buffers. We've got our chunk position that's used to set the vertices at wherever the chunk is supposed to be. And then our container size for use during our flattening process. So now we move on to the fun part. Here is where we pack our float values for smoothness and metallic into floats so that they can be read on the shader. These are functionally identical. The only difference is one takes in a float 2 because I'm lazy. We have a function to unpack floats into float 2s via bit shifting. That was mostly used for debugging, but it might be useful in the future, so it's staying in. We've got our flatten chord, same as we have over in the voxel generation compute shader. We've got our voxel is solid check, which just checks our voxel array at a flattened index for position. And if the ID doesn't equal 0, then we return true, else we return false. And then here is our actual mesh generation function. Similarly to our voxel generation, we have a check for if any id.xz, so if x or z is greater than container size x. So if we're above 16, return, and if we're below 1, also return, so we can get that seaming around the chunks working properly. Then we cache our voxel block for the coordinate we're running right now. If the block is solid, we'll go ahead and continue with the run. Then just like in container, we have our cached values or cached arrays, sorry, for our face vertices, face UVs, and because it's the same all the way across a block, we have our color here. And then we pre-initialize our vert count and try count for use during generation. Then we go ahead and iterate over all 6 faces. We check if the face in that direction is solid. So take our position, add the face check or face direction to it. If it's solid, continue. We don't want to deal with this face. If it's not, and we want to draw the face, we'll increment our counter, and then we'll add 6 to our vertex and triangle counts. This is actually not going to be used until we get to the next episode when we get to contouring and a shared vertex configuration, which I will actually show you a demo of at the end of this video. So we interlock our counters, and then we interlock our counters, and then we get all 4 vertices for this face. Same thing as container pretty much. And we add our local coordinate ID here, and then our chunk position. And then we iterate over all 6 parts of the quad, add them to our vertex buffer, and our color buffer, and our index buffer. And our color buffer here, we assign B and A to be our UVs, because it's the only way I could get them to interpolate properly on a shader. Because if you didn't know, when you're using a vertex shader, as it travels from one edge of a triangle to the next, it will try to interpolate between all the values. So if you have red on one vertex and green on another, it'll change in like a rainbow in between the 2 colors. Might be a bad example. I don't actually know what it looks like when you interpolate between red and green, but so setting it to color A and B is the only way the UVs were moving properly. And then we assign our color buffer to be that color. And excuse me, I missed a part up here. When we initialize our color, our cached color, I actually pack the metallic and smoothness for our block ID from those voxel colors into our G of our color. So R is our actual color and its wonderful float form, and then G is our metallic and smoothness variables. So, assuming I haven't skipped anything here, which I might have, but I don't believe I did. Let me double check. You should now have an almost functioning project if you try to run it. But there's one more change we need to make here. We have to come over to our shader again, which is, I'm sure, everybody's favorite part, and we need to modify it a little bit. So we'll take our vertex colors out, split it, and then we will take the R value and run it through a custom function. All this function does is take our input of float, which again, because our voxel colors are now compressed into a single float value, and then we bit shift all the way back across, so shifting to the right 8 bits, 16 bits, 24 bits, and pulling those values back out of the float and dividing them by 255 because they're multiplied by 255 when they're packed. Then we output that as our color, pass it into the fragment, and then we also have our G value being split into the other pack method, where we get the modulus of inputs for our Y. Our output X is floored inputs divided by 100. And then we divide that by 100 minus 1 just to bring it back out of that range, assign our X and Y, and pass it into our metallic and smoothness parts of the shader. I'm not going to pretend to be that smart. The packing methods here were found with a little bit of Googling because bit shifting is not my cup of tea. But now if we go ahead and run the project, you should see, takes a minute to allocate all that data. But now we should have our 64 by 64 chunks rendering, or whatever you went and assigned your render distance to. You may have to reset your colors in World Manager. You'll have to reset them because they're changed color 32 colors, so your world might be black when you first run it. If it is, don't panic. It's the world colors. You just need to go reset those. It's kind of the issue of doing this from a git diff, but now you can go explore your world. It should actually look pretty similar to mine right now, but you can go through the seeds and see what other sites there are. You can also mess with the existing noise functions that are in and see what you can find and see what looks good. I'm sure there's many people out there who can make better looking terrain than I did, but that's neither here nor there. I'm just making the method to show it. And now, because I promised it earlier, and I've already showed a sneak peek off on Reddit, which thank you, anyone from Reddit who's here now, for all the subscribers and views. It was absolutely wonderful to see that kind of response to the contouring method that I'm finally getting to in the next video. So we'll go ahead and flash over to that project. Let me get that open real quick. And I'll make sure all my settings are good. Bump that up. And then we wait for all the allocations. What's this? They're not squares anymore? What's this? It looks very low poly. Yep, that is my contouring method. It's definitely possible to convert it to generate smooth terrain. I, however, like the low poly look. That's why it was the first one I implemented. But this will be part 6 of our series. We'll actually get into contouring finally, and I won't be a liar anymore, because I'm sure everyone's like, well, all this guy is doing is making Minecraft. But I'm not. I told you in the first video I had some contouring to show you guys. And here I'll show you the shared vertices rendering, which is used if you want that slightly smoother look. I haven't actually looked at what it does to the memory. It should be about the same though. So as you can see, you don't see every triangle anymore. Still see it a little bit, but it's a lot more smoothed out. Same world, just a smoother look, less low poly, more stylized, as you will. So that's all I have for you guys today. Thank you for bearing with me on this extremely long video. I did make a Patreon recently. I don't really expect anyone to go there. I'm still a new channel and all that, but if you do like my videos and you want to have features like being in a Discord, asking questions, chatting with other people, or if you want immediate source code access as I'm working on these projects, that's also a reward for one of the tiers. So any in-dev stuff, once it's, actually functioning, I'll push it to Git and you could see stuff weeks in advance, even if there's no video accompanying it yet. I'll also be trying to get videos onto Patreon at least a day early moving forward. So yeah, it'll be a good time. Again, I don't expect anyone to actually go subscribe over there, but hey, if you like the videos, feel free. I'm not your manager. But thank you everybody for joining me on this episode of our Voxel Generation series, and I will see you guys in the next video.